So we would like to move on to the next session. The next session is TSN. The first, we have one presentation for this section. The title is Real Life Performance of IEEE 1722 Control Format. The speaker is Pablo Granados from CETITEC.
Thank you very much. Thank you very much as well to the organizers and the committee for allowing us to be here. So let me start with a couple of questions. 1722 ACF, who has heard of it? Okay, so and of those of you who has actually had practical implementation, sort of a proof of concept or something like that? Okay, yeah. Well, we were in a similar situation where we hadn't had any real experience with this. We thought it was really interesting. So we decided to have our own hands-on with it. And we want to present our findings and our observations here to you today. And this is how we're going to do it. First of all, this is going to be basically just a recap of what we've heard this couple of days prior. Why we consider this to be an interesting approach when moving from conventional networking systems into more like what we are going to see in the future. We're going to go over to a benchmark scenario that we prepared to assess the performance of ACF communications compared to basically just UDP. And the previous presentation had a very good overview of those two systems, so that was quite convenient. We'll go over the results that we obtained in our general observations, and we identified also as well a couple of optimizations possibilities that we see in this context. And to finalize all of this, we'll present what we have experienced so far with ACF and what we see as the scope of future work. So current automotive systems, most of them are structured in what we would call the domain architecture. Access to the ECUs and sensors are handled here in each one of these domains. This is also quite efficient in terms of if you want to, if you consider handling the real-time specific constraints of each domain. But communications going from these ECUs here to a different domain controller or a different ECU require gateways, and it's mostly signal-to-service translations. The conventional communications in the controller, of course, CAN, LIN, and FlexRay. Now, the transition to zonal architectures, this is basically a recap just at this point because we have been seeing that quite a bit. It really, as we saw in a couple of presentations before, the efficiency in the translation from information from one of these zones into the rest of the zones or the central computer would be, or the central computer would be really, or is really important, that it's done in an effective way, that it's done in an efficient way. So all of this appears to be appears to represent the conditions for ACF communications, since we can rely on existing ABB and TSN mechanisms that are already quite widely used, widely available, And we have all the added benefits thereof, since, for instance, the timing information can be preserved or restored in case that is necessary. We have also, we can reduce the overhead in the device where data from these conventional networks is acquired. So basically right here, that tends to be a performance hotspot. And we can do this while maintaining or potentially improving performance. So if we apply ACF to this concept, then messages here from the conventional networks would be aggregated and sent over ACF to both the central computer and other zone devices with basically no extra overhead. The signals will be extracted where needed, and all of that while timing information is, again, preserved or can be reconstructed. And if we think about this, also the section here about the data producers, and they have high performance requirements since we are dealing with very short messages coming from the sensors or actuators, and these are produced with a high frequency. So in this constellation, those data producers could be also optimized because it's very simple to send aggregated messages or ACF. And the data consumers can use this information and repackage it in case it's needed. Also very important, information going back to those ECUs and actuators can be sent back over ACF as well. And just to reiterate, we have the mechanisms from ABB and TSN to help us set priorities or bandwidth reservation, since all of that is already available. The deterministic mass transit time is also quite an important feature that comes with this. So much for the theory. Now, we always want to get our hands dirty and basically pull things apart, see how they work, and pull them back together. So that's what we set up to do. So we went ahead and defined a benchmark. And if we consider our representative here part of the zone with one zone device in a central computer, basically, an estimate is that between 90 to 96% of all the routing operations are still CAN linked to Ethernet, with Ethernet being with CAN being around 80% thereof. So this is basically our base configuration that we want to explore. We'll have then the data producer, of course, on the zonal device, and the data consumer on the central computer. And we wanted to determine performance as a function of resource consumption. With real devices, this looks like this. We took an approach. We selected two devices that we had at hand, our very own CETITEC. It's just a known platform. It doesn't have any fancy optimization for networking, so I think it's a fair comparison. It does have very good ABB support, just ABB support for streaming. And with this, we can create a system where we have a known platform, and we can just explore the difference in this section right here, transport. That's what was of interest to us. So we'll have two CAN inputs here to the first CETITEC, simulating the zone device. And the output will be sent over Ethernet to the receiving application here on the second SETI box. The receiving application extracts the data to simulate overhead. And this is how it looked like, the stacks inside the SETI boxes. In this case, basically we have the CAN driver receiving the data, and we have a conversion from CAN to UDP. Basically the most straightforward, cheapest, efficient conversion that we could do, as was shown before. That data is packaged very simply and sent over Ethernet to the second box, which takes it out and doesn't do anything with the data, just unpacks it and generates some overhead. In terms of the payload, this is actually how it looks like. And for the test configuration, we took the two CAN inputs, each one with 100 messages per second, and each with 8 bytes of payload, and generated 3 different load scenarios with 10,000 messages per second, 50,000 messages per second, and 20,000 messages per second. All of those were just achieved by multiplying these inputs, basically copying those messages here. We also added interference traffic here, 5,000 messages per second over TCP with a light payload, just to see what impact would it have. Now with ACF, the picture looks a little bit different. We prepared our CAN to ACF converter, so to say, and we had to modify our standard ABB audio talker to do ACF. We have our GPTP master in the SETI box number 1. It doesn't really matter where it was, but place it here in the bridge. And this one is also doing the switch configuration for the device. And on the receiving device, we have basically the opposite of the stack, the GPTP slave and the ACF listener. Now, the payload looks basically the same. We take the same inputs on CAN, and we multiply them to achieve the different message loads, 10K, 15K, and 20K. Interfering traffic with 5,000 messages per second was also applied here in this case. And yeah, by the way, we were using ACF class C with 750 messages per second. Now, results that we obtained, we normalized everything here to the reference level of 10,000 messages per second using UDP. And in case of the ACF talker versus the sender using UDP, when this upper section here is when we don't use any interference traffic, and as we can see, basically there is no difference in performance. Yeah, by the way, this plus would signify performance detriment, and a minus would signify a performance benefit. So again, without interference traffic, we couldn't observe any significant change. When using the interference traffic, it seems a little bit different. We actually see a minor performance gain when we use ACF. Now for the listener case, it actually looks pretty similar. It's again normalized to the receiver using UDP here to 100%. And as we couldn't establish any significant changes in performance when either of those was used in the absence of interference traffic. When we had interference traffic added to the mix, then we basically saw that with larger throughput, there seems to be a slight benefit when using ACF. but again, not too significant. So the fact that we couldn't find any significant performance difference was interesting to us, but we want to actually reiterate on what is actually obtained and all the mechanisms of ABB and TSN can be used. So we think this is very interesting. The last point here is, of course, subjective to us. So we think it's a relatively easy way to achieve this message forwarding. It actually doesn't have to. We had to do quite a bunch of things to get the benchmark with UDP. I don't want to say we tipped the scale in that direction, but to get it really efficient, we had to use quite a bunch of components that we have. And with ACF, basically the packetizing is already there. It's quite easier to it's quite easy to use. So one of the other things that we consider with this setup, and I think that actually goes in the direction of all the discussions that we were having yesterday, when we think about a software-defined vehicle, is that sometimes it's better to control what traffic is sent. And perhaps the best interrupt is the one that doesn't come. So what we saw here as a potential is that maybe we don't do just this conversion every time we get canned messages, or just for every message in the same way. So maybe we can achieve a better performance by selectively using the communication channel. That would give us also flexibility to adapt to different scenarios, and perhaps even easier configuration workflow. And our answer to that, and that's what we are working on currently with one of our car manufacturer customers, is what we refer to as a distributed data system. So it's basically the concept of a non-relational in-memory database that can be used to simplify the data producer, and you can have a flexible database deployment throughout the system, if you think about the zone, that actually would allow us to just request the data that we need when we need it. Data throttling and filtering would be included and could be done in an easy way. And of course, since we have GPTP here, we can timestamp all relevant communications. Again, as the case that was shown before, was discussed before with the dead reckoning and wheel ticks, that's a perfect candidate for something like this. And we can use ACF for communication between these the in-memory databases for this simple and reliable data transfer. So far, in our experience here with ACF, no surprise, we can establish that it has the additional benefits of ABB and TSN mechanisms. That this ABB part is really widely available in current hardware systems. It's simple to use, and data can be packaged really easy and efficiently. And I know that there are some approaches to even make that easier to do by having hardware support. All of that can be added with a layer of flexibility and further improved if we use our approach and package the data selectively, maybe even on a signal level, and with data throttling and filtering even at the producer. For future work, we see that performance could be further evaluated with different scenarios and criteria. And of course, there are optimizations that can be done in several different ways for the ACF talkers and listeners. Also, what are the implications of different ACF classes? That's also very interesting. And combining all of this with a distributed data system, that's what we'd like to pursue in the future. And with that, I want to thank you for your attention, and I welcome your questions.
Thank you for the presentation.
Hi, I'm Don Panel of NXP, but I'm going to put a different hat on.
I'm sorry. I'm almost deaf right now.
No, I can talk louder.
Yeah, go ahead, please.
I'm Don Panel of NXP. I'm going to put a different hat on right now because I'm the secretary of IEEE 1722 and the current editor of 1722B. So that's why I raised my hand and saying I'm familiar with this. Did you use the time synchronous control format or the non-time synchronous control format header on ACF?
We use the time synchronous.
Okay.
Yeah.
So you were doing a single message in an Ethernet frame, single CAN message in an Ethernet frame.
Well, yeah.
No, I'm just asking. I mean, so
Yeah.
because you can also do the time synchronous control format and have multiple CAN messages in an Ethernet frame,
Right.
where each CAN message has its own timestamp on it.
Right. In this case, since they were basically injected.
No, that's fine. I'm just asking what you were doing because then you get that optimization of bandwidth by packing multiple things, and you still preserve the timestamps.
Exactly. That's what we like about it.
And did you use 1722 raw or the UDP IP UDP version of 1722?
No, the raw version.
Okay, because a lot of people, unfortunately, we put that in Annex J, and a lot of people think that 1722 is only layer 2, yet there is an official, you can run it on IP UDP for people that need to do that. So, thank you, that's all I had.
Thank you.
Any other questions?
You know me, right? I'm Hoài Hoàng Banh Xuân from Overcast. Also, this similar experiment. But of course, if you pack one CAN frame in one Ethernet frame, then you get a similar performance. No surprise. But isn't it the whole point of 1722 is that you achieve the deterministic behavior you have from transport layer directly to the layer 2? You can skip the network layer. So you from application from talker, you generate a frame. You can send directly in layer 2 Ethernet. In the UDP case, you need to go via IP. Did you measure any latency?
What we did was to normalize everything to a particular, that's why we made it a function of the input messages. So to transmit the input messages in the same way, so the payloads were the same. Yeah, we tried several. I know what you mean. We tried several different order benchmark combinations, and again, if you are, we were doing here the packetizing for UDP quite efficiently, quite lean, and if you don't do that, then the performance difference towards ACF is immense. I mean, we were measuring like at least 50% performance increase. So that's why I said we kind of put things harder for ACF. We try to, push the scale a little bit. But still, I mean, we have those advantages, like what you said before. Those are the important things, like deterministic max transit time and so on.
My second question: did you have any problem when you with the startup when you do ACF channels? Do you have any problem with startup time and the time that you need to establish the channel?
Not really, but we were not considering like a startup scenario or something like that. We just establish the communication once what's running.
Okay, thank you.
Any questions? 2 minutes remaining. Okay. Thank you, Pablo.
Thank you so much.
So let's take a coffee break.